Here in this video we continue our discussion of logic gates. Previous video we looked at the NOT gate, or the inverter, where the output is always the opposite of the input. In this video we look at the AND gate, which performs the logical AND function, and the logical AND function is explained right here in this truth table. This is a 2-input AND gate. You can also have AND gates that have more than 2 inputs. But if you understand this 2-input AND gate truth table, you should be able to understand the truth table no matter how many inputs you have. So if you look at this 2-input AND gate truth table, you can see that the output is a 1 only when both inputs are a 1. If any of the inputs are 0, or if both are 0, well, you get an output of a 0. And this is true no matter how many inputs you have. So if you had 4 inputs to an AND gate, it would take all 4 inputs equal to a 1 to get a 1 out. If just one of those 4 inputs was a 0, you get a 0 out. Okay, now this is the symbol for an AND gate, and over here is the circuitry of an AND gate made out of Mosfets. You can also make an AND gate out of BJTs. It would basically, you would just replace each one of these Mosfets with a BJT switch circuit like we saw in previous videos. Now here's some Boolean algebra. This dot here means the AND function. So you would say that this output is A ANDed with B. And again, the AND function is explained right here, where all inputs would have to be a 1 in order to get a 1 out. Otherwise you get a 0. So what we're going to do next is we're going to show how this truth table is achieved with this circuit here. Each of these transistors, each of these MOSFETs is being operated as a switch. So remember, when you're operating a transistor as a switch, the input to the transistor, which is the gate voltage for this MOSFET, can only be one of two values, either a 0 or 1. And then from drain to source you have your channel, and when that voltage is one value, the channel acts as an open, and when it's the other value, it acts as a short. So we're just doing the ideal analysis here. So where we have zeros and ones, a 0 is 0 volts, a 1 is plus voltage, which is enough voltage to make this channel ideally a short. So let's use this diagram over here to do our analysis. So the way this diagram is shown right now is with V1 and V2 both being 0 volts. Okay, so 0 volts on the gate of this MOSFET, 0 volts on the gate of this MOSFET. So if you have 0 volts on the gate of a MOSFET, like we talked about previously, that means you're not going to have a channel. Okay, these are enhancement mode MOSFETs, like we've seen before. So both of these MOSFETs at the input, inputs, is going to be acting like an open between drain and source. Well, that means that there won't be any current flow from this source VDD, this 5 volts here, right? Because in order for current to flow from this source, it needs a path to ground. And it doesn't have a path to ground through here, since both MOSFETs are acting like opens from drain to source. And also the current won't flow this way, because remember, at the gate of a MOSFET you have very high impedance. Okay, this is the gate. Okay, so because of that high impedance, no current's going to flow this path either. So what that means is that you have 0 current through this resistor, okay, which means the voltage across it is also going to be 0. And when you have 0 volts across something, it means the voltage is the same on both sides. So you're going to have 5 volts here where the source is, 5 volts at this node on the other side of this resistor, which is the input voltage to this MOSFET. And that's going to cause the drain to source of this MOSFET to act like a short, which is going to connect V out right to ground. It also provides a path for current to flow from VDD here, and the entire amount of 5 volts is going to be dropped across this resistor. Okay, and V0 is going to equal 0 volts. So you see when both inputs are 0, you're going to get 0 volts, which is a 0 out. Now, the next two rows of the truth table, okay, we'll bring back our truth table over here. Okay, so you see we just proved this first row. When both inputs are 0, you get a 0 out. Well, the next two rows of the truth table, one of the inputs is still 0 volts. Oops, I moved the wrong thing here. Okay, so now in the second row of the truth table, see V1 is still 0, so this one's still going to be acting like an open. V2 is a 1, 5 volts, so this one's going to be acting like a short. But you see, even if just this MOSFET's acting like an open, it's still going to prevent any current from flowing, just like we had in the previous case, and it's going to keep 5 volts on this gate, which is going to keep this a short, and V0 is going to stay at 0. Likewise, if V1 is a short from drain to source and V2 is open, well, same result. Still current won't flow through this resistor. We'll have 5 volts on the gate of this MOSFET, and V out is still going to be 0. So that's why for the first 3 rows of our truth table, the output is 0, because at least one of these input MOSFETs is an open, okay, which keeps 5 volts here, and again keeps this channel a short, which keeps V0 a 0. See, it's only when both inputs are 1. So let's go to a different color here. Okay, see, it's only when V1 and V2 are both 1s, or both 5 volts, that we're going to get a different output, because now both of these channels are acting like shorts, and that connects this node right to ground. So current's going to flow through this resistor from this source VDD. You'll get 5 volts dropped across that resistor. You're going to have 0 volts on this gate, and when you have 0 volts on that gate, it's going to make the drain to source of this MOSFET an open, and when it's an open, there's not going to be any current through this resistor. There's going to be 0 volts across that resistor, and now your output's going to be 5 volts. Okay, so that's why in the truth table you see that you only get a 1, 5 volts out when both inputs are 1. Now the last thing here before we end the video is that if you had more than 2 inputs to an AND gate, it would require additional transistors at the input. So for example, a 4 input AND gate would have a total of 5 transistors, because you'd have 2 more transistors connected up in the same fashion as these 2 are. This is essentially a series type of connection with these transistors. So you'd have 2 more right in line, right in series with these 2 for a total of 5 transistors. So every time you add an input to an AND gate like this, you need an additional transistor. And you'll see throughout the digital block of this course that I'm often referring to how many transistors are inside various logic circuits, because I think that's important, because at the end you'll start to understand why it's a big deal when microprocessor companies like Intel come out with new microprocessors and brag about how many transistors are inside. You'll see that all this circuitry we talk about in the digital block are found in microprocessors.